So hi everyone, thanks for joining the EXA's webinar series on digital solutions for electric vehicle design. So today's webinar is going to focus on the aeroacoustic solutions for electric vehicle design. So before I get started, let me introduce myself. I am Siva Senthuran, Senior Director for Aeroacoustics Applications at EXA. So in this role, I'm responsible for the development and deployment of aeroacoustic solutions. So this job has given me the opportunity to work with several OEMs worldwide in understanding their design process, understanding the challenges that they face, and work together with them on coming up with a better design solution that could help them design better vehicles. With that, let me start with the presentation. So in today's automotive market, electric vehicles are breaking new grounds. So we see announcements from major OEMs about their initiatives towards electric vehicle design. In addition to major OEMs, we also see several startup companies working on electric vehicles. So what is driving all these OEMs towards electric vehicle design? So one of the major driver towards vehicle electrification is the regulations. So here we see regulations imposed by several countries to ensure that the transition from internal combustion engine to electric vehicles happen in a short time frame. This is mainly done to control emissions and reduce global warming. So automotive OEMs are reacting to these regulations. So they are announcing their commitments to developing electric vehicles, and also they are switching major engineering resources towards getting this technology developed so that they are ready when the time comes, and also they can keep up with the competition. So when you're switching to the new technology, it comes with a lot of challenges, but these challenges also create opportunities. When those challenges are handled right, they are going to create opportunity for us to become market leaders and become brand differentiators. So let's talk about those challenges now. So when it comes to electric vehicle design, we can think of three major challenges. One is customer expectation, and what we mean here is customers expect the vehicles to be quiet. In addition to better range, safety, reliability, and attractive design, they want the vehicles to be quieter. And the other one is the architectural freedom. So here we are talking about any new wind noise issues that could come due to new design layouts of electric vehicles. And the third one is competition. So electric vehicle market has created room for new OEMs. We see several startup companies competing with major OEMs for the same market share. So now let's discuss these three challenges in a little bit more detail. So let me start with the customer expectation. Customers want the vehicles to be quieter. So they make this very clear in all the surveys. So what you see here is the 2016 Vehicle Dependability Survey from J.D. Power. So you can clearly see excessive wind noise is one of the top complaints by the customers. So if you look at any recent surveys, you will see the same thing. You will see excessive wind noise is one of the major complaints. So automotive OEMs react to this one. So they pay attention to this one, and they put a lot of resource into making the vehicles quieter year by year so that they can satisfy the customers and also keep up with the competition. But this gets more challenging when it comes to electric vehicles. It's mainly because there's a widespread perception that the electric vehicles are extremely quieter than the internal combustion engine vehicles. So there are several articles that represent the same perception. So what you see here is an article from MIT Technology Review, and as you can see here, the author is talking about how electric vehicles are extremely quieter compared to the internal combustion engine vehicles, and they create the greatest danger to the passenger when they move slowly because they are very quiet. And this is very true, but this doesn't represent all the driving conditions. So the question that we have to answer is, are electric vehicles always quieter under all driving conditions? So of course at lower speeds, electric vehicles are going to be quieter than internal combustion engine vehicles because they don't have the engine noise. They still have to deal with the noise from electronic cooling fans and battery cooling fan, but the noise levels are much lower than what you would get from and engine noise. The plots that you're seeing here compare the noise performance of internal combustion engine with electric vehicles at different speeds. And there are two studies here. One is done in Europe and one is done in Asia. And you can clearly see from these plots that at lower speeds, electric vehicles are very quiet compared to the internal combustion engine. But when the speed changes, you can see the trend is changing. The noise levels start to get closer and the difference is shrinking. This is mainly due to at normal cruising speeds. Now the tire and wind noise are going to become more important. And these contributions are similar for electric vehicles and internal combustion engine vehicles. So when the speed increases further and we get to a higher speed, wind noise is going to take over. So wind noise is going to be the dominant contributor to the interior noise. And by the time we get to this speed, there's no difference in the noise performance between electric vehicle and internal combustion engine vehicle. This means engineers are under great pressure to reduce the wind noise because they have to meet the customer expectation of electric vehicles being quieter than internal combustion engine vehicles at all driving conditions. So the other challenge that we have is the architectural freedom. The absence of engine and powertrain will create more space for designers to work with to explore different designs. Also, electric vehicles have reduced need for cooling, which means the grill opening can be eliminated or greatly reduced, which means the designers have more option now to explore different design, very big changes to meet styling and performance requirements. So big changes in the design means there's a possibility of new wind noise issues. So wind noise is created from separated flow structures from the geometry. So when you make the shape change a lot, you could end up changing the flow structure significantly, which could create additional noise issues. And also because of some of the big changes, you could end up even create new separated flow structures that could add more noise. And also when you make big changes to the design, we could end up putting high-speed flow close to the ceiling, which means more noise could come in to the cabin through ceiling and make the noise levels go up. We also have seen some examples where customers are trying flying surfaces, and these flying surfaces create gaps and cavities, and they create resonance that could annoy the customer inside the cabin. So what all these mean is any experience we have developed from any design best practices that we have developed from internal combustion engine vehicles may not be applicable in the future when we start going towards more and more electric vehicle designs that are going to change a lot in shape. So the third issue is new competition. The electric vehicle market seems to be attracting the investors a lot. So we see a lot of investors putting a lot of money into electric vehicle market, and this could be mainly due to the worldwide success of different electric vehicle companies that are doing well. So for example, we can talk about Tesla in North America and BYD from China. The availability of more capital is creating more startup companies working on electric vehicles. The challenges that here is when you have new startup companies means they may not have the established noise control process that the established OEMs may have. And also some of them may not have the same level of experience that the established OEMs have. But at the same time, on the positive side, this means they may be more open to new approaches. And when you're open to new approaches, this may allow them to address noise challenges more effectively and come up with a quieter vehicle. So we talked about some of the new challenges that we are going to face with electric vehicles. At the same time, we also have the existing challenges that we still need to face when it comes to electric vehicle design. So one of the existing challenges that we continue to face is the availability of prototypes. The early stage prototypes are not suitable for acoustic evaluation, and by the time we get a prototype that is good enough to do aeroacoustic evaluation, the design is mostly frozen. So we only have freedom to make small changes, and we only have little time to make those changes to influence the exterior shape of the vehicle. In addition to that, the integration effects of fans and HVAC system on noise also cannot be evaluated when you don't have the prototype early enough. The other issue that we have is identifying the noise sources. Let's say that we have a major noise issue. Now, there are not enough techniques available in the traditional testing environment to identify the noise sources and understand what needs to be changed. So because of those challenges, sometimes the noise issues don't get addressed early enough, which means it leads to late-stage fixes that are not optimal. And when they are not addressed sooner, then it could cause launch delays that cost a lot of money to the OEMs. So these challenges create the needs for solutions that could address those challenges. So we can talk about what are the possibilities of addressing those challenges with new solutions. So at EXA, we understand all these pains that customers go through when they design their vehicles, and we have developed a solution to address those challenges and help engineers design better vehicles more effectively. So our solutions start with the concept of start early and fix easily. What this means is we have an option of starting to evaluate major designs from very early in the design process, even before the prototype is built. So when we start early, the design is not frozen, which means any time we identify a major issue, we have an option, a larger design space to make changes and make the vehicle quieter. So what this means is by the time you get the prototype, major noise issues will be identified and fixed, and now what we have to do is to verify some of the design decisions that were made and make refinements to meet targets if needed. So by doing this, we can develop better designs at lower cost and minimize any late-stage failures. So let me explain the benefit of the EXA's PowerFLOW solution for aeroacoustics using a greenhouse wind noise example. So the image that you see here is representing the noise inside the cabin coming from greenhouse wind noise. So let me play a sound file first. So the sound that you heard right now was the noise that a passenger sitting inside the car is going to hear due to greenhouse wind noise. So EXA solution is going to allow us to predict and hear the noise inside the cabin very early. So once you can predict and hear the noise, then we can actually quantitatively and qualitatively assess the shape of the vehicle. So once we have this quantitative assessment done, then we can come outside the vehicle, now start looking at what is happening on the panels and what's the load that's coming inside the vehicle to contribute to the noise that we hear inside the vehicle. So in this particular example, the color map that you see on the glass shows the acoustic loads on the glass that's contributing to the noise inside the cabin. So anytime you see a dark red region, which means there's high acoustic load at that point, that means if you want to make the vehicles quieter, we need to make those red regions go away or shrink them. So once we have identified the hotspot that we want to work on, then we can use some advanced visualization techniques that we have developed, such as FIND, which stands for Flow-Induced Noise Detection, which identify the acoustic noise sources, to identify which flow structures are creating the acoustics that are contributing to the loads and contributing the noise inside the cabin. Once you have this understanding, you can narrow down into those flow structures and understand which part of the geometry is creating those noise sources and make informative design changes. So this reduces the design space that we have to work on to make the vehicles quieter. So once we have this information, this visualization explaining the noise issues and the impact the design change is making, so we can effectively communicate this to the studio to ask for the design change. So what you see here is the typical noise sources that we see in an internal combustion engine vehicle. So we have noise coming from greenhouse, underbody seals, buffeting from sunroof, side window, component noise, HVAC noise, underbody and exhaust noise. So there are several noise contributions that contributes the noise that's heard inside the cabin. So now we come to electric vehicles. We can see we pretty much have the same noise sources. Nothing has changed, except there are two noise sources that go away. One is the engine cooling fan noise, that's not there anymore, and also the exhaust noise is not there anymore. But at the same time, we have picked up two additional noise contribution. One is from the battery cooling fan, and the other one is from additional electronic cooling fan. So what you're seeing here is showing all the digital solution that we have developed at EXA to help with the electric vehicle designs. And today our focus is going to be on the blue region that represents the Aeroacoustics. So if you look at the outer ring, it shows all the available solutions, and with all these available solutions, we should be able to address all the noise contribution that we talked in the prior slide that we have to face when it comes to electric vehicle design. So now let me go through each of these solutions one by one in a little bit more detail. So now we are starting with the greenhouse wind noise. By the way, you're going to hear some noise that's actually representing the noise what you're going to hear when you sit inside the cabin. So when we talk about greenhouse wind noise, here we are talking about the noise sources that are generated due to the exterior shape of the vehicle, transmitting noise through the glass panels and heard by the passenger or driver inside the cabin. So this is a well-established application. It's used widely by engineers for vehicle design. So there are several publications out there showing the accuracy and how it's used in the design process. Some of them are published by EXA, some of them are published by customers. So the toggle image that you see on the right-hand side, that shows the available design space if you implement a digital solution early in the design space. So you can see if we implement this early, we have options to make changes to the sheet metal to make the vehicles quieter, so we have better design options to address any noise change issues that we have. So what's going to be different? What are the implications when it comes to electric vehicle design? So as we discussed before, just like internal combustion engines, electric vehicles are going to have the same wind noise issue. The wind noise is going to dominate at higher speed. Because customers expect these vehicles to be quiet at all driving conditions, we have to make the electric vehicles more quieter than the internal combustion engine vehicles. So if you look at the shapes of current electric vehicles, they do not change much compared to the internal combustion engine vehicles, which means we need to make more aggressive changes to the design to make them more quieter than the internal combustion engine vehicles. But we have changes coming. So there are discussions about changing mirrors into cameras and eliminating mirrors. So in certain regions, certain countries, this is approved already. So taking a mirror off is definitely going to help because it takes one of the major noise sources away. But at the same time, it could make some of the noise sources become stronger. For example, the air pillar vortex could become stronger. So which means we had to think about different design changes now to make those noise sources quieter. Then we can, if you think about the future shapes, we already get some glimpse about what designers are thinking, and we see they're thinking about very big changes. So when you think about very big changes, which means the design best practices are not going to be applicable anymore, which means we could end up with more potential noise issues. So implementing a simulation-based solution early in the design process and evaluating those big changes will allow us to identify any major issues early enough and fix them with better design changes. So one of the other major wind noise contribution is from underbody wind noise. So here we are talking about flow separations in the underbody region, creating strong noise sources, and these noise sources get into the cabin through underbody panels as well as wheel wells. So underbody noise is very strong in the low to mid frequency, and it definitely needs more attention. But underbody design is mainly driven by aero performance. So what we can do here is we can assess any design changes that are done for aero and come up with making sure that they're not going to create any new noise issues. So the design space that typically customers evaluate for underbody wind noise is shown here in the toggle image. So when it comes to electric vehicles is going to get a small break from underbody wind noise mainly because of the batteries that are placed in the underbody, which adds more mass, and that can actually reduce the noise that's going to come inside the cabin through the underbody panels. But at the same time, from the image that you see here, which obtained from the acoustic visualization technique FIND, shows the majority of the acoustic noise sources are around the wheels, which means these acoustic noise sources can get inside the cabin through the wheel wells, and this needs to be addressed to make the vehicles quieter. So as we discussed before, the major changes, design changes are going to be driven by aero, and by having a digital solution, we'll be able to screen those changes and make sure that we don't run into any major issues when it comes to underbody wind noise. So another aeroacoustic solution that we have is gap and seal noise. So this is the newest solution that we have released. So this was came out this month. It's very exciting and unique application. The reason we say that is because the noise that comes into the cabin comes through glass and seals. So we can do all the thing right and define a perfect exterior shape, but if we don't pay attention to the seals, more noise could come through the seals and make the vehicles noisier. So this digital solution for seals allow us to assess the impact of design on the seals and make sure that we make design changes to keep the loads away from the seals so that we can make the vehicles quieter. So the toggle image show here that all the options available in terms of changing the designs to keep the loads away from the seals to make the vehicle quieter if we implement a solution early in the design process. So when it comes to electric vehicle, the major challenge for gap and seal noise could be for the new OEMs because they don't have an established noise control process for seals or design process for seals. And because of that, they may have to start, inventing this, on their own. So anytime the design changes a lot, using a traditional test process, we don't have an understanding the amount of load it's going to have on the seals. That's mainly because when you have a prototype, you don't have a seal because the seal design is done very late in the design process. So most of the design decisions are made with taped condition, and when you have taped condition, you're actually ignoring the amount of noise going to come through the seals because of the design that you have. So by using a digital solution and assessing designs early in the design process, we could actually make changes to keep the strong loads away from the seals so that we can improve the noise performance. And also late in the stage when we are starting to design the seals, we have an option to think about where to put double or triple seals based on the proximity of those seals to the high noise sources. And also we can think about where to put cavity blockers to reduce cavity resonance. And also we have options to study about manufacturing variation and think about where we want to be safe to put multi-layers of seals without increasing the cost by putting it everywhere. So another aeroacoustic solution that's available that will be very relevant to electric vehicle design is the component noise. So component noise, what we mean here is that many components that get added to the exterior shape of the vehicle, and they could create flow separation, create extra noise sources that could come inside the cabin and make the vehicles quieter, make the vehicles noisier. The movie that you see here shows how an exposed wiper could create flow separation that could create noise sources that's going to be heard inside the cabin by the driver and the passenger. So the toggle image here shows some of the other components that create noise sources, such as deflector that stick into the flow region, spoilers, roof racks. So when it comes to electric vehicles, there are a lot of components are being thought about or being evaluated to improve the aero performance of the electric vehicles to improve the range. But some of these examples are C-pillar blades and flying pillars, and these aero enhancements could create noise issues. And also, the next generation of electric vehicles will be autonomous vehicles, and here we are going to have sensors on the roof, and the movie that you see here shows one of the sensors mounted on the roof, and sensors like this could create massive flow separation and create extra noise sources that could contribute to the noise inside the cabin. So having a simulation, a digital solution early in the process to screen and evaluate these designs will provide us an opportunity to make changes to those ideas and those components and come up with a better component that will reduce the noise inside the cabin. So another aeroacoustic solution that needs to be considered for when we design vehicles is buffeting. So here we have sunroof and side window buffeting. What we mean by buffeting is, in this case, we have a window that's open. We have a clear flow on the exterior, which will roll into a vortex, and it could impinge on the rear lip of the opening. And this is going to excite the cabin. When the excitation frequency of the shear layer matches the excitation frequency of the cabin responds very strongly and creates the buffeting behavior. When this happens, it's very painful, and this needs to be eliminated to give a better driving experience. So buffeting is very difficult to catch early in the design process because early prototypes have more leakage. When you have more leakage, the vehicles don't buffet. So by the time you get very late in the design stage and the vehicles become more tighter, that's when you can reliably test and predict the buffeting performance. But by that time, it's going to be too late to make any design changes to address buffeting. So when it comes to electric vehicles are moving towards more rounded shape to improve the aero performance and increase the range. And also, we talked about the chances of moving towards mirrorless vehicles, which means the shear layer on the exterior is going to be very clean, which means it could roll into a very strong vortex and provide a strong excitation through the opening to the cabin. If this happens, we could end up with a much stronger buffeting issue. That means electric vehicles have more risk of buffeting compared to the current internal combustion engine vehicles. So as we discussed, it will be very difficult to catch till late in the prototype, and by the time it's going to be too difficult to make any changes. So by implementing a digital solution, we have an opportunity to screen any major design changes that we are thinking early enough to address them through design changes. So another aeroacoustic application that needs to be considered is the fan noise. The noise that you're hearing here right now is the noise that you would hear if you are walking next to the vehicle that's passing by, and the noise is coming from the fan. So with the fan noise solution that we exist here, and here we are seeing a cooling fan noise example here, we can actually design the blades and the fan to reduce the noise. But in addition to that, we can also evaluate the integration effect of fan and try to provide a better noise performance. So when it comes to electric vehicles, as we discussed, we don't have the issue of engine cooling fan anymore, but we do have battery cooling fan that needs attention. So the movie that you see here shows the noise generated by the battery cooling fan. So in addition to battery cooling fan, we also have several electronic components inside the vehicle that needs to be kept cool to avoid failure, which means all those electronic component fans are going to create noise. The issue that we have is because these components are distributed everywhere, it's not easy to mask. The only way to address them is by better design. And also some of these electronic equipments are close to the passenger, which means they are going to hear the noise very well. So these designs need to be improved to reduce the noise. So doing a simulation early enough allows us to study the performance of the fan standalone, and also study the integration effect to come up with a better design to reduce the noise. So we talked about all the challenges, and we talked about all the solutions that are available to address those challenges. And so what can we do with that, or what engineers are doing with these solutions? So let me explain that by showing some success stories. But before that starts, let me play a movie that shows what is the impact that we could have by implementing a solution early and making a change to the exterior shape, to changing the sheet metal shape of the vehicle. So here you're seeing the acoustic waves from the panel showing the loads created by the shape of the vehicle. And from the acoustic maps, you're seeing two distinct hotspots on the glass, and flow-induced noise detection saying this is coming from side mirrors and the A-pillar vortex. So obviously we'll work on a side mirror, but in this case we decided to make a change to the sheet metal by changing the cross-section of the A-pillar. And you can see, because the design change, you can see a big reduction in the acoustic noise also generated by the A-pillar. So now when you come inside, you can see such a change could give you about 2 dB reduction in the interior noise. So what this means is, starting early and making changes to the sheet metal provides a big opportunity for us to make the vehicles quieter through design change. So another example that we see here is electronic cooling fan. We mentioned that electronic cooling fan is critical for electric vehicles. So here you're going to see an example of what we could do by using a simulation and how we could improve the design of electronic cooling fan. So the noise that you hear is actually showing, what you're going to hear if you walk around this fan geometry when it's under function. So now we are identifying the noise sources created by the fan using flow-induced noise detection technology. So it's pointing to the outside shape of the blade. So here it's pointing us to the region where we need to make a change. So you can see a design change has been made which reduces the noise sources a lot, and it's actually reducing the noise that's going to come from this fan. So let me take you through a few customer success stories quickly. So the first success story talks about how a better design could be obtained by implementing a digital solution early in the design stage. The visualization that you're seeing here is not from the actual vehicle. It's a representative of what happened in this particular case using a different vehicle. So in this particular case, this OEM found their vehicles to be louder than their competitors, mainly in the high frequency region. So they want to make changes to improve the noise performance, but they find it's going to be difficult to do that using experimental process only, because they don't have enough freedom to make design changes by the time they get access to the prototype. So in this particular case, they decide to use a simulation technique to guide the design change to these vehicles. So changes were done to the side mirrors, A-pillar, and the hood of the vehicle in this particular case to change the flow that gets directed towards the mirror and the A-pillar. By making such big changes, we were able to get 3 dB overall reduction in the interior noise with only a few iterations of the design. The second success story talks about designing common mirrors. So common mirrors are widely used by OEMs to cut cost. And in this particular case, this particular OEM wanted to use the common mirror strategy, but at the same time they also wanted to improve the noise performance of their vehicles. So they considered 2 models here for this common mirror, and they decided to use the simulation to help with the design of those common mirrors. So in this particular case, we tested the mirrors digitally on both vehicles, and based on the visualization, we identified the changes that need to be made. And from the changes that were made, we were able to get 2 dB overall reduction in the interior noise from design changes. So these design changes were confirmed in the test later on, and they got signed off for production. So the other custom success story comes from wiper placement. So we talked about how an exposed wiper could create more noise and make the interior become noisier. In this particular case, this OEM lost a layer of prototype due to process streamlining. So which means the engineers had to make a decision about where to place the wiper without testing because the prototype was not available. So they decided to use the simulation technique for them to guide to make the design decision here. So they tested different wiper positions using PowerFLOW simulations and came up with a design that will meet the component target for wiper design. And due to the success of this particular effort, now that was implemented as their standard vehicle development process. So the last success story comes from a roof rack design. In this particular case, a roof rack design needed to be redesigned to address howl noise. In this particular case, the OEM identified a howl noise very late during, very close to the launch process. So they had 2 weeks time to make a decision about what to do with this howl noise. And it's not possible to do design changes and address this issue using test only. Therefore, they decided to use PowerFLOW in conjunction to the test to come up with a decision. So 11 different design configurations were assessed using test and simulation, and by the end, 10 dB reduction was achieved in the howl noise, and by combining test and simulations together, they were able to get the feedback faster at low cost and able to avoid the launch delay. So we talked about many challenges that we are going to have with the new technology, and we also talked about the availabilities, the possibilities that are available for us to address them using all the options that we have. So let me finish with this closing remark. If we imagine all the possibilities, what can we create together? So thank you for your attention. I will be happy to answer any questions that you have.